So today we will have Grant Fleming, and the topic will be AI alignment considerations for data science practitioners. Before I go to introducing Grant, I would like to also let you know that our next event, our next speaker will be Eric Ma. Eric is a principal data scientist at Moderna, supporting research data science. So as you know, Moderna is one of the big companies that come up with the vaccine, and he is working as a data scientist there. So he is a really, really good speaker. So please don't miss that event. It will be on April 29th. Okay, before further ado, let me introduce one more time Grant. So here, Grant is a data scientist at Elder Research, and his professional focus is on machine learning for social science applications, model interpretability, civic technology, and building software tools for reproducible data science. Okay, so in addition to his excellent career, he is also author of Responsible Data Science book. So a co-author of the Responsible Data Science book. This is from Wiley Publishing. So I will be sharing the link again in the chat window. So please take a look at it. This is an excellent book, and please, I think you should definitely take it, and then you can enjoy his also expertise in responsible data science field. Grant, you can take on. Thank you so much for joining us.
Thank you, Murat, and thank you for everyone at UMBC who's involved in getting me here and setting up the infrastructure to allow me to speak. I really appreciate that, both just to talk to anyone enthusiastic about data science in general, but talk more specifically about AI alignment, responsible data science, whatever terminology you want to use for that. As Murat mentioned, I'm going to flip to the next slide real quick for a brief moment of self-promotion. There is a book that I've co-authored out, and it is called Responsible Data Science. You can find it on Amazon, Wiley, or what have you. But yeah, I'm a data scientist at Elder Research, and I've been in this field for a little over 3 years now. And as part of those responsibilities, I had the opportunity to write this book, and it's been a great experience to learn about these topics and be able to talk to people about them. So with regards to this presentation itself, I want to caveat before I even say what's on this slide by saying that I hope that these slides, in addition to being a good basis for a presentation here, and that being interesting and all that, I hope that I can send these slides over to Murat or folks at UMBC so that you all can download these slides for yourself and use them as a resource. I've put a lot of hyperlinks in here, and I've made a very bloated appendix for a lot of the tools or sort of theoretical proofs or methods that I'm discussing in this presentation. And I hope that the presentation itself, it gives you some idea of what all those are, but really you see this more as a jumping off point for you to learn more about this. And hopefully, anything you see in this presentation, and if you download the presentation after and follow any of the links, hopefully that gets you further along that path. So hopefully at the end of this call, Murat, we can talk about me getting these slides over to you.
Exactly. And very quick remark, everyone who signed up for the event will get the recording and the slides of the talk. Okay, so our team will reach out to you hopefully within a couple of weeks, and then you will be receiving the event details. Okay.
Excellent. Awesome. Thank you, Murat. Well, all right. Thanks all. How is this going to proceed? Well, first, we're going to go ahead and give you the main takeaways. So I don't want to bury the lead here. If you need to jump off, really early for lunch, or your child needs attention, or you're only a few minutes in, but you're still not quite interested, I want to go ahead and give you the main takeaways that of all the things that are going to be talked about over this hour period, I hope that you walk away remembering. After that, we're going to talk about discussions of future-facing concerns about AI. So the things that people in certain positions of power and influence in tech and in academic research institutions are worrying about that may be relevant in maybe the next century. And then we're going to look more towards the present and review practical tools and approaches we can use to help mitigate AI risks that exist now and have existed for a while. So what are those takeaways? First, the harms of AI models are not consigned to a dystopian future or the imagination of futurists. They are real and present today. And I'm going to hammer this point home repeatedly over the course of this presentation. AI is a silver bullet for certain problems, but for a lot of other problems, it's dubiously effective. And even for the ones where it is effective, it's pretty easy to cause harm. These modeling harms, however, occur most often as unintentional consequences of these models behaving in ways that do not align with our goals. So most people who use AI models that end up causing harms from the predictions those models make, they don't mean to do that. They don't want people to be misclassified as a gender they're not supposed to be, or be given a prediction that harms them in a material way. It's just a consequence of the AI system not aligning with the goals that we've set out. And maybe we haven't set these out explicitly. Third and finally, these harms are not necessarily things that we are stuck with. We can leverage certain technical and social best practices to diagnose as well as mitigate some proportion of the risk associated with using these models. And through the course of this presentation, we'll go through some of those. But first off, let's talk about what people who think about the future are worrying about with respect to the future. And that's going to be AI alignment in discussion as it's discussed in these halls of power today. The first thing that people are worried about, and probably what is propagated the most through media, is fears of superintelligence. Anytime anyone thinks about AI fears, it's pretty common, at least in a US-based context, to think of something like Skynet from Terminator taking over the world with all these subtle machinations of people's motivations here, controlling some weapon system there, and basically treating us all like cattle. And there's a lot of worry today amongst certain people that this is going to be a reality that we have to face in the next few decades or the next century. And there are resources being spent on mitigating this problem in the present. But the other big area people are worrying about is AI alignment. So regardless of whether or not you end up with a super intelligent AI in the future, if you end up with an AI that is sufficiently powerful or has sufficient influence over the real world, there can be all sorts of consequences from that AI model not understanding the goal that we want it to actually pursue. So one example that is commonly discussed in literature is literature being like fiction, more for pop reading versus academic literature. The one problem that's often discussed is the paperclip problem, where imagine you have a production AI that is told to maximize the efficiency and quantity with which it can produce paperclips. And this AI ends up not just producing paperclips very well with the resources it has, but it leverages systems outside of what it was supposed to leverage to make more paperclips, and ends up basically drowning the whole planet in paperclips because that AI ends up having a lot of influence. Again, this is kind of science fiction, but it's something that people worry about. And on the slide, I'm not going to read off all these, but these are a lot of the different parties, being research institutes or private companies or individuals who are all thinking about this issue and writing about this issue. And again, all the blue text here are all hyperlinks to their pages or relevant research on these topics. So if anyone's interested, again, when this presentation is over and you have the slides, you can click these links and follow and read more about them. But the gist of it is there's a lot of powerful people and organizations worried about this issue. Well, that's fine in one sense, but it's unclear when, say, superintelligence will become an issue. Anyone who's worked in the field of data science, we can probably tell you that one word we would not use to describe the models we build is superintelligent, and that more generally having a model or AI generalized to a task beyond what it was trained on is a very difficult thing to do. In fact, there's a lot of disagreement over when this will happen from experts. I have a link here There's a big survey done of hundreds of experts, and there's a pretty bimodal distribution centered around 2036 to 2060 for these experts saying it'll happen by then. We'll have super intelligent AI that can bootstrap and iteratively improve itself, become smarter and smarter. And then the other half of experts saying this will never happen, or at least not in a timeline that's relevant to our lives. So it doesn't give me personally a lot of confidence that this is something we should be worrying about or focusing a lot of time thinking about. However, on the AI alignment front, there's evidence that this is a present and growing issue, and you don't have to take my word for it. On this slide here, I've listed just a few headlines that I found through crawling the internet for various articles writing about issues of AI algorithms causing harm intentionally. And there's all sorts of cases in health, in law, in finance, in lending, in surveillance, where well-intentioned actors fit a model and did the best they could to make that model accurate and performant. But what ended up happening is that model made predictions that caused harm in the real world. And as a result, there's been all sorts of media fallback on that. And so I would argue that this is a present issue and that we need to be thinking about this, because even if your model does not cause harm such that you're going to end up in one of these news articles, it makes sense that we would want to understand our models and have them align with our goals. And if we're using a traditional modeling approach, it's kind of hard to make that happen. After all, when you're doing a traditional modeling approach, non-technical considerations like the business context, it's listed here in this. I believe this is the diagram for CRISP-DM, which is a relatively widely used data science paradigm. But outside of this one, business understanding or real-world context is often not included as a consideration. Evaluations of model performance, they're often too simple. Maybe they focus on one metric, or they follow error metrics, but they don't look at the directions of those errors across groups. In addition, it's not often incentivized for us to understand how the model works. That's a problem, and we'll make that point a little bit more throughout this presentation. And then deployment itself is treated as the end of a pipeline rather than as another step. Any of us who've worked with models and have deployed them into the real world where they're going to make decisions that impact the real world know that data drift, changes in where the model is used, and changes in the real world all alter how our model is going to perform and require us to iteratively refine the process of gathering new data, refitting the model, and having it adapt to these new circumstances. So beyond that, I would also argue that there's all sorts of poor incentives in the field now for why we are often seeing these harms. For example, there's a dearth of meaningful regulation or accountability of AI applications, at least in the US. There have been a few states who passed laws around this, and there have been national level organizations that have put out guidance, but it's voluntary. The EU is currently drafting their AI Act, which should end up being enacted in 2023. But right now, there's not a lot of accountability. There's, in research, a lot of state-of-the-art metric chasing and single metric primacy. So it's a pretty big incentive for a lot of researchers to be able to put in a paper, hey, we build a model, it actually performs better on this one metric by some maybe marginal amount. And that is our primary contribution here, because that gets them a lot of attention and credibility. Beyond that, reproducibility is pretty uncommon. Only about 15% of AI studies share their code, according to this report from 2021. And more specifically, it's just very hard to replicate these big models and this research done by these large organizations where they spend millions of dollars on computing resources to fit their models, which individuals like yourselves or myself cannot easily do. Model interpretability is a niche interest, as I've mentioned, and there is also a large bias towards bigger, more opaque black box models. Add more layers to the network, add more neurons, add more skip connections. That is what excites people versus having a model which is easy to explain. So we need to think that we can't control the work that others do, which in this case might be helpful sometimes because we can prevent some of these harms. But beyond keeping the conversation around alignment going and pushing for regulation, we can focus on our own work. And if we want to do our work more responsibly, we need to more rigorously align our own models to our own goals and desires. We can't control what other people do, but we can control what we do. And we can do the work that we do better than we do it now. So think about it this way. At least this is how we argue to think about it in our book. And this is a sort of frame of mind that seems to have caught on in research and seems to be pretty popular. AI alignment is a theoretical discussion, as it is often talked about in media and in research. The practical application of that you can think of as responsible data science. And people use other terms for this. You may hear trustworthy AI or model governance. There's all sorts of different ways to call it. But when you hear responsible data science or similar, you can think of that as the practical application of this AI alignment work that these futurists are concerned about, and that we too should be concerned about. And we can develop that understanding and intuition for how to do responsible data science ourselves by building up from the bottom. So here we have a very reduced form of a typical data science model. You have the model pipeline. You have the data, you have the model, and you have the predictions. Very simple. Altogether, these together are the technical factors that are relevant into a modeling pipeline. And I would make the argument that typically these are most of what we consider, or at least what we spend the most time considering. Responsible data science asks us to do better than that. It asks us to consider the social factors at the start, and these can be, the business understanding, the real world context, what resources we have available, who's on our team, legal compliance, and social factors at the end, which, asks us to consider, are our models and results reproducible? Do individuals or groups impacted by the model have any recourse to change the predictions? And just generally, what's the impact? And from a responsible data science perspective, when you have all this together, what we need to do is say, for these technical factors, we need to improve the rigor, scope, and efficacy of what we're already doing. And then for the social factors, we need to consider them as an important part of the process in the first place. Altogether, that gets us responsible data science. Which leads us to part of the presentation where I talk about how we actually do this, because I don't want to just sit here and grandstand and say, hey, we should be more ethical, we should be more responsible. We need actually some advice on how we can make that happen. So we'll focus on this in kind of reverse order. We're going to go from looking at diagnosing and mitigating bias in predictions, then we're going to go to the model, and then we're going to go to the data, because you can do different things in each different component. Starting with the predictions, we want to think about some relevant questions here. And this is how each of these is going to progress. I'm not going to go through all these relevant questions, but basically, if you're doing this correctly, you should be able to answer all these questions in a way that's either affirmative or be able to say, yes, we're doing this. Yes, we've hit this metric. Yes, we're doing this fairly. But when thinking about diagnosing bias at the prediction level or the level of predictions, I think one really good example that happened in the real world is the controversy surrounding the Compass recidivism prediction algorithm that ProPublica wrote about in 2016. Basically, this algorithm assigned either bail or let people basically go back onto the street after violent crime based on the perceived risk from the perspective of the model of them committing another violent crime within 2 years. And even though this model was well calibrated and highly accurate, it ended up leading to predictions where a lot of white individuals who ended up committing violent crimes in the future were let go, and they were they weren't held on bail, they were let out into the street. And a lot of Black individuals who did not go on to commit crimes, they were held on bail. So the model discriminated against them by holding Black folks on bail more often than white people. And we can actually see this bias for ourselves. We went through this example in our book, and I've adapted some of those figures here. So first off, this is a plot showing two models that we used in our book to actually predict the 2-year recidivism binary yes/no ourselves. And you're seeing performance metrics here for different groups. So for example, the model is roughly 70% accurate on Caucasians, maybe a little bit more than 70%, if you look at logistic regression and random forest averaged together. And then for African Americans, it's ever so slightly less accurate, but not that much more. We'll just say it's roughly 70% accurate overall. Now, and this is where the responsible data science comes in. We know that overall metrics can hide biases within our data. If we switch from using something like accuracy across groups to a better metric, like say false positive rate across groups, we can see a pretty significant difference here, where from before it was maybe 1 or 2% different for each model. We now see that the false positive rate for African Americans is in some cases almost triple than it is for Caucasians. And I'm sorry that I'm switching between white, African American, Black, etc. Easy to just flip through those. So apologies if that's a little unclear at times. But yes, this is a difference that's highlighted just by using a different metric. And if we had only looked at accuracy, that would have not made this clear. But we can make it even more clear by taking that same metric and say, okay, we're not caring too much about the absolute value if we're thinking from a fairness perspective. We want to see how each group is affected by these predictions relative to a privileged group, which in this case is going to be Caucasians. So if the Caucasian baseline, you could draw a vertical line up from 0 on the x-axis, reach a certain level of error, how do the other groups perform relative to it? And here you can see that for African Americans, especially for the logistic regression model, that false positive rate is almost 175% higher. And this did not take a lot of work for us to see. Took a bit to get the code working, but from a modeling perspective, it was fairly simple. And these are things that we can easily do in our own models if we choose to look. So yeah, this disparity is most clear in comparing the relative metrics. And if we think about this from a broader perspective, you can show that bias. I can go back to this plot and say, okay, this is very clearly a biased model. It's biased against certain groups. In fact, if you fall into another ethnicity besides Hispanic, African American, or Caucasian, you're actually getting an error in the other direction. It's letting you go even more often than it is white people. But how do we actually mitigate that bias? And I'm not going to go through all these methods here, but again, when you get this PowerPoint, you can click through and see things for yourself. There's a lot of options here that exist now and are already coded into software packages that we use in Python and R to allow us to mitigate this bias once we know it's there. And we did that here. We actually took the prediction thresholds that say, okay, if the model predicts a probability of recidivism over, say, 0.5, we're going to predict that you're going to recidivate, so we'll assign you a positive class versus a negative class. And we actually optimized each of those thresholds per group. So if we go back to the previous slide, this would be looking at the method in the first bullet point, or one of the methods that would fall under that first bullet point. And you can see this most clearly when you're looking at, and I should have highlighted this, but the bottom on the legend where it says model, optimize JSTAT, optimize manual, original, if you compare the original bars, the differences between them across groups versus the differences between the groups where the red arrows are pointing, you can see that the groups being pointed at by the red arrows are much closer together. And that's indicating that our optimized threshold, even though it did reduce performance for the privileged class, in this case Caucasian, or actually no, it's equivalent here, my mistake, but it made those performance metrics much more equal. It can sometimes make them worse for certain classes, but in the end, what you get is a situation where the model is getting roughly similar false positive rate across all groups, which is something we would want. It's what's fair, it's what's ethical, it's what's responsible. And so it's a good sign. This can work. This isn't just all talk. It's not just things that we can solve in the future. There are things we can do today. And that's just at the level of predictions. When we look at modeling, there are things that we can actually change in the model function itself beyond the prediction thresholds to diagnose and mitigate bias. And if we want to be able to affirmatively say, yes, we've done that, we've made sure that our model is at least minimally certain to not produce a certain amount of bias, these are the questions we need to be able to answer. And so I'll just leave this slide up for a second or two. And to be able to answer those questions, I and other practitioners in this field make the argument that we need to be able to interpret what our models are doing. We need to be able to say, we know how our models take certain features and take certain values of those features and how much influence those feature values have on the prediction it makes. Because if we don't know which features the model finds important, it's going to be very difficult to predict what sort of behavior it'll have when it's deployed either in the real world or used on new data. And one canonical example of how this can be helpful is from the local interpretable model agnostic explanations paper that Marco Tulio Ribeiro published in 2016. It shows for a deep neural network, a CNN specifically, that was misclassifying huskies as wolves, where the model was looking, quote unquote looking, I'm doing air quotes here, and I know no one can see that, but where the model was quote unquote looking and why it made that error. And we can see that it was classifying it as a wolf, not because of anything to do with the husky itself, which is what we would want the model to look at, but to do with the snow in the background. And this is the sort of behavior that by having either local interpretability, where we look at individual predictions and say what happened here, or global interpretability, where we look at the average effective features on predictions, this allows us to debug our model and make changes further down the pipe or earlier in the pipe that can prevent these issues from happening. And another funny example of this would be in February 2021, a few people were publishing articles on YouTube's toxicity detection model, detecting discussions of white versus black chess strategy, and actually banning discussion around that in the comments and in the videos because the toxicity model has assigned a very high toxicity score to the word white and the word black. So in this context, a lot of chess grandmasters or chess streamers, whoever is making these videos, they were kind of confused as to why their content was being flagged as controversial and getting pulled, but this would explain that. This is an example of what we were seeing on the previous slide, where YouTube, in this case, maybe Alphabet above them, was not properly debugging their model and did not know that it would have this effect. Or if they did know, they did not do anything about it. And we can also see this in an NLP context where there are packages that exist now, like Captum for PyTorch or TF-Explain for TensorFlow, where you can take a output from, say, a transformer model, and maybe it assigns a sentiment score, a toxicity score to a particular sentence, and you want to know, okay, well, which words were the most influential? There are methods that allow you to look at that, both at a per observation level and at a global level when looking at the model as a whole. And here, again, I know this is a wall of text. Clients at work would not like to see this, but this is more of an academic context. I don't expect everyone to look at this and absorb this, but again, hopefully this is something where you can look at the slides later, click a few of these links and learn more about these methods. And assuming we have time for questions, I'll blaze through this if I need to. Anyone's welcome to ask me about any of these. But diagnosing, as we know, is one part of the problem. We want to actually mitigate that bias. And fortunately, there's a lot of work that's been done so far, both in academic research and in practical contexts, to mitigate bias that is occurring within the model. And you can do this by taking a pre-trained transformer model, for example, and fine-tuning it on a specific data set that maybe was constructed to be more diverse or be less biased. This is something that OpenAI has been publishing recently in their work with Instruct GPT, which is an extension of their GPT-3 transformer text generation model. It is a little bit less toxic and is better able to follow human instructions. You can have the model resample or weigh certain data points in the training data differently so that you kind of mitigate some of that bias in how the model is trained. And then there's regularization terms and various different constraints that you can declaratively state in the model's objective function within certain software packages. They'll prevent it from treating certain features as important, or will prevent it from allowing certain feature values to have negative impacts, which in cases like race, if race is a feature in your model, you don't probably want a individual value of race to have a negative impact or a positive impact. Ideally, it would have no impact, but that's not how the world is, unfortunately. Finally, we get to looking at the level of the data. And in the responsible data science research and discussions that are happening now, this is referred to as pre-processing. And I don't think I mentioned this for the previous ones, but when you're looking at it from the level of the data, people call it pre-processing. So pre-processing for diagnosing and mitigating bias. At the model level, it's in processing because you're processing within the model itself. And then predictions is post-processing because you're diagnosing and mitigating bias after the model has made its predictions, and you're making those changes before those predictions go out into the real world. And again, I'll give us a few seconds here to look at relevant questions for the data. And when we're thinking about diagnosing bias at the data level, I would be remiss not to include mention of Joy Boylan-Weeney's work in 2017 on the Gender Shades project. So this was a project that she did as a master's student at MIT with Timnit Gebru, who at the time was a PhD student at Stanford. And as darker skinned African-American women, they both realized in their own personal lives that facial recognition algorithms for things like Snapchat or anything that creates a facial filter, you know, for quote unquote fun uses, were having a very hard time recognizing their faces relative to their friends who had lighter skin. And so they decided, okay, we're going to take some off-the-shelf algorithms from these large tech companies, and we're going to create a benchmark data set of a diverse set of faces pulled from various different parliaments, including many parliaments from Africa, and test these models to see if they have more error when predicting the gender for dark faces versus light faces. Sorry, I should have been entering here so that you actually got the text so you could follow along. But yes, they did compare the performance of 3 facial recognition algorithms at identifying gender, so binary, you know, male, not male, female, not female. And you can see in this image, which I got from their website, that again, depending on what you consider to be an acceptable accuracy metric, each model performed fairly well overall. At least, you know, the largest delta here is a little bit less than 6% between the Microsoft model and the IBM model. So they all did within the same ballpark of each other. But as before, in the Compass recidivism example, the bias became evident when they looked at the predicted performance and error rates across groups. So I'm not going to take you through the protracted discussion that we had with the Compass example. I'm going to jump straight to the, I guess, the conclusion here. But when you look at the image here on this slide, they are showing that lighter males in the, sorry, I don't want to give you a number, and I should have highlighted this, but there's the lighter male column in the middle. They clearly have the highest performance, aka the least error, and the darker female column directly to the left of it very clearly had the lowest performance, the highest error across all models. And this gap in error rate was huge for all of them, you know, going between roughly 21 and 35%. And that's, you know, a little sad because these are big tech companies with a lot of resources, a lot of smart, well-meaning people who should be able to solve this task in a way that's roughly equitable. But despite all those resources, despite what I don't doubt are good intentions, they still ended up with these models that had these large error disparities. And this was something that at the time created a lot of controversy in the news. This paper has been cited thousands of times, and at least it's one of the first times in my memory that I can recall this sort of bias being discussed in sort of a public setting that did not have the technical background for talking about AI or something like that at a practitioner level. And so these companies actually were compelled to put out responses. A lot of them made arguments saying, oh, actually, it's not that biased. You know, you got it wrong. You should have measured it this way. But what ended up happening, despite what these companies were actually saying, was that by 2019, when Deb Raji and Joy Buolamwini did follow-on research to see, have these companies improve their algorithms at all, they actually did. And I should have gotten an image here to show you a metric from their paper, but effectively what they found is that in addition to the Microsoft facial recognition algorithm, the Face++ one and the IBM one, all becoming more accurate overall. So that would be, like in this case, going from 93, 90, and 87.9 to maybe 98% for all of them. In addition to becoming more accurate overall, this error disparity was massively, massively reduced. It basically was cut down by like a factor of 2. I think the largest disparity, if I'm remembering now, between lighter skinned males and darker skinned females in predicting gender was right around 5%, which, you know, it's still a measurable difference. The models still are biased towards lighter skinned males, but it was a massive improvement. And it only took them 2 years to do that. So then the question becomes, okay, well, how did they do this? What did they do as a result of this research being published that they were not doing before? And what I would say here is I would make the argument that really all that they did, this is probably not all that they did, but maybe the most important thing that they did is they trained the model on more data, and specifically a more diverse set of data. And other researchers have made this argument and have shown it to be a true phenomenon. And it should ring, I think, intuitively pretty true to us. If you want your model to predict well on a specific logical grouping within a data, within a set of data, whether that's a demographic grouping for predictions about people, or whether it's something to do with geography, you probably do not want to train your model only on one group and then have it predict on a group that it's never seen before. And researchers have shown that. They've shown that to be true in the case of facial recognition. And in this image here on the slide, we can see the ethnic breakdown of various facial recognition data sets. I don't know, and I don't believe any of us will ever know what facial recognition data sets those companies had trained their algorithms on, but it was not the Fairface data set. It was likely one of the data sets listed on this table. And as you can see, this Fairface data set of face images for facial recognition is much more ethnically balanced. And so hypothetically, you would expect a priori that if you trained a facial recognition model on a random sample of data from Fairface, you would end up with a model that has less of an error disparity than a model trained on one of those other data sets. And for our book, we did that. So we went into PyTorch, we said, we're going to solve this for ourselves. And we fit these ResNet 18 convolutional neural network models to samples from the Fairface data set. And we did this on 2 separate models. A balanced model, where the balanced model was a random sample from the Fairface data, which got us roughly equal amounts of faces from those different ethnic groups listed in the previous slide. And we did a model that sampled data such that we ended up with a proportion of faces belonging to ethnicities roughly representing the proportion that those ethnicities are represented in America. And we did this based on the American census, which at the time, I think was the 2010 one. So unfortunately, we didn't have the most up-to-date data. But basically what this led to is us training the census model on roughly 76% white faces, and then, you know, a lower percentage of each of those other ethnic groups. And again, you know, we would expect that the census model, if our hypothesis about training on diverse data being important, if that was correct, we would expect it to perform worse, specifically on groups that it did not encounter much, or at least not to the same degree that it countered other groups, in this case, white men. And we can see in this false positive rate parity plot that that was the case. Most of the groups that were, I'm sorry, I'm trying to orient myself here. So the model performed worse, not just on faces that tend to correspond with darker skin on the Fitzpatrick scale, which is a dermatological scale of like average skin darkness. It not only performed worse for darker faces, but it tended to perform worse for women, even white women. You can see that kind of in the middle of the plot there, where for white females, the census model did almost 20% worse than the balance model, and that these disparities were pronounced over all these different categories. And that alone, we think, shows that more diverse data, irrespective of anything else you do with the model, is helpful. At the data level, that's what we should be thinking about. All right, and that leads us to the social aspects now. So we've gone through the technical aspects and how we think in a responsible data science, you should improve your rigor there. And now just going to really briefly touch on how we think we need to improve rigor on the social aspects, starting with the social aspects that occur after the predictions are made. And again, 1 or 2 seconds for the relevant questions. I'm not going to go through all the different points here, but again, when your model has been fit, you're making predictions and those predictions are going out in the real world. Hopefully by that point, you've considered the risk versus utility of your model, the quote unquote impact. So for example, you hopefully by now, if you're doing something in deep fakes where you're taking face data from one person and swapping it into a video or image to make that person in the video look like someone else, you're hopefully reconsidering the benefit of that when that technology so far has mostly been used to create doctored revenge porn and fake online personas and video for propaganda purposes. Certain applications like that, I would argue, are just not worth the risk, regardless of how interesting they are. It's also important at this point to be considering recourse, whether anyone who the algorithm makes predictions about, whether they have any opportunity to say, hey, I don't think this is right, I'm going to appeal this decision, or if they don't have an avenue for appeal, they're at least given a recommendation for how they can change their behavior in such a way that the prediction then becomes a prediction that's positive for them. And one such example here that generated a lot of controversy is that the A-level exams in the UK, I believe it was 2018 or 2019, were canceled because of, well, no, it couldn't have been then. It must have been 2021 because of COVID. They were canceled because of COVID, so students could not take them. And the UK government decided, okay, well, we're not going to just jettison the need for A-levels. We're going to assign students A-level scores algorithmically based on what they think or what we think they would have scored on this exam, and that will affect their college admission opportunities. And for students who are given poor scores, either because they went to, by whatever measure the UK government was using, lower quality school, then maybe they felt like they were justifiably given a bad outcome, one that they didn't deserve. And they did not have any recourse to appeal this decision. And from an ethical perspective, I think that's a huge loss. Beyond that, it's just helpful to have transparency over your data, your models, how your models perform, what they should be used for. If you do, or if you give people access, then there's all sorts of knock-on benefits, follow-on benefits. Twitter did a image cropping challenge where after there was controversy generated over their image cropping algorithm, it would attempt to crop images to white faces or like lighter colors versus darker colors. So cropping out darker people. they wanted to actually fix that, and they were able to host this challenge and pay people to actually come up with solutions for them, which won them not just goodwill from a public perspective, but a much better anti-cropping algorithm. So that's great. And obviously, being more transparent and knowing these problems are out there is great, I think, because it creates useful impetus for regulation. And I do think that the field of AI is one that does require more regulation than we currently have. And finally, we go all the way back to the start of the process, the social factors here, the relevant questions, and then thinking about what these are. And I'll end, this is the last slide. I'll end by saying that there are legal issues currently with using certain algorithms in certain areas, both from a business sector perspective, but also from a geography perspective. But moreover, that regulation around the world is coming down the pipe, and that it's unlikely that this field is going to be able to get away with a lot of the excesses that we've had up until now, and that these harms will have legal liability in the future. It's not an if, it's a when. And I think that's as good of a note as any to end on. So I will end by saying thank you all for listening. Sorry if this ran longer than expected, or if I sped through certain areas that I should have spent a little bit more time on, but I'll briefly mention there's an appendix. It has a lot of links, just like the rest of this slide deck, and that I hope at least one of you takes a look at this and finds it useful. Appreciate your time, and I'll be open to any questions.
Thank you so much, Grant, and now you give us a lot of reading homework. It's really super interesting, and I definitely want to go and read all these very interesting stuff. So we have a couple of questions. If you don't mind, I will go through them very quickly, and time-wise, we have 8 minutes left. So Ming Yu is asking, for the three aspects that you mentioned in your presentation, changing metrics, model, and focusing on predictions, focusing on model, and focusing on data, which one of these things most important? And they follow up with but the data diversity is not always possible, right? Some kind of data are harder to get, some may be rare events. What would you say about that?
Yeah, and that's a fair point, especially with the rare event, I guess, point that individual had made, that this is the reason that a lot of time series models broke down over COVID, because, regardless of how much historical data you had for that sort of modeling, you're not going to have a global pandemic event in your historical data that you can learn from. I mean, you do now, but you didn't at the time. And so what's important, I think, at that point, and this is going also to the first point of the question, is getting a more diverse, robust set of data if you can, if it's available, and spending significant resources to do so if it's not immediately available. But in some cases, like you mentioned, there aren't going to be that data. Like, they just do not exist. There's no amount of money you can pay to get them. And so in that case, oh man, can flip back. I don't know if this is going to be easy to remember for anyone. But this is where the set of methods that come at the bottom here on this slide, the domain knowledge constraints and the constrained condition models, come in, where if you do not think you're going to get data that are going to represent some situations which can happen in the future, there are opportunities, and there is software available now that allows you to declaratively state if this new condition happens, or provide some sort of domain knowledge where, with this logic, you know that the model, when it encounters certain situations it hasn't seen before, or certain data it hasn't seen before, it will behave off a set of priors. It's not just gonna, fit to something wild that you don't expect. And that would be my best advice there.
Okay, great. And we have one more question about, how do we differentiate data diversity from outliers in a data set? This is Lee Chuan. I hope I'm not butchering your name, but yeah. So what would you say about that?
Hmm. Yeah, so that is something that I think is extremely context dependent. It's a great question to ask because it's a question I think we're asking often in work that we do, at least that I do on the day-to-day basis. It is something where you are best served, I think, as a data science practitioner or as someone with a technical background to defer to people who have any domain expertise. If you're working in a domain where you, for example, like in public health or in certain logistics sectors or in maybe mental health, if you're looking at surveys, where the domain expert can say, oh, hey, this is a true outlier. Maybe you should process it in this certain way or trash it or create artificial data to populate within the model more outliers like that so the model can adjust to them. But in general, I would say you should defer to uh, subject matter experts there if they're available.
Okay, perfect. We have 5 more minutes left, and I don't see any other questions. I do have a question and comments, Grant, if you don't mind. And I wish in the future maybe we can have also like a more like a panel type of like a conversation type of thing. It was a great presentation. You did it, and it's really amazing. And Mingyu-san, it's again, if you registered for the event, you will get the presentation and the recording of the meeting. Okay, so someone from our team will send you the link, so you will be able to get the resources. Okay, so one thing is with the diversifying the data, I have a comment on, we can check the the groups that is already, we know that there are groupings, right? So for example, demographic data is one thing, or like gender groups are one thing that we can definitely check. And then you make it a very clear point, like do the best practices, right? There is no like a silver bullet type of thing. But I'm also like wondering what kind of things and research should be done for the groups that we are not aware of yet, right? So, like, or we do not pay attention enough. There are lots of underrepresented groups, and we might not even notice this thing in the public yet. So, for example, and one thing is class, right? Socioeconomic classes, right? So how do we represent this data, or like if we have racial, demographic information, socioeconomic classes, and then let's say gender groupings. So how do we combine these concerns, and like how do we check these things in an algorithm? I don't know whether I could explain myself when I ask my
No,
question.
no, that makes sense. It makes sense, and that it is a great question. It is also a very hard question to answer. I would say that the best practices around that now it's kind of a mix of things, right? I guess that's always the case for these. But first off, even though a group may not be evident in the data, like maybe it's not recorded in some way, or we don't know as data scientists that these observations can be divided into logical groupings. That's something where if we're working with a subject matter expert, that may be clear to them. And so being able to have those discussions with them and have them be an involved part of the process and point out cases where there may be groupings that we don't see is critical. And I would say that that's something that in my own work, I wish my clients would be a little bit better at. Wanting to be involved in that way is what I mean specifically. But beyond that, it is possible for us to identify these groups on our own. You can look at correlations between features, and in my own experience, anecdotally, I don't have any research to back this up, but in cases where groups aren't evident, I can find correlations between features that are strong enough that after the fact, I notice that they are groups. And I guessed at the time that I saw the correlations that they would be. So looking at correlations is helpful. And then more generally, I think for any model that you're going to deploy into the real world, you want to do a lot of testing internally. And fortunately, that's something that I think is pretty heavily encouraged. But when you're doing that testing and seeing the predictions and analyzing the predictions and maybe where the model is erroring and like what sort of feature values are more likely to be associated with the model creating an error, whether in a regression context or a classification context, you can sort of at that point go back and make hypotheses about, well, maybe these are groups and I can add that as a feature and see whether that feature is predictive or not. And that can be useful.
Okay, thank you. And I would like to ask one very quick question, and then we can close this thing. Do you know whether the Google, Facebook, Microsoft type of companies has something like an ethics engineering type of positions? Like it sounds like this is a very technical, someone with very technical skills in both ethical and also computer science, and should be hired to check and test this kind of stuff. Do you know these companies are hiring this kind of folks?
They are. Yeah, absolutely. And you're totally right, I think, to highlight that it's a very specific set of skills here. You know, you need both the computer science ability to actually make the code that will allow you to make these changes to the models and write functions that will allow you to diagnose these issues, but you also have to have the sort of sociology, almost political science, economics background to be able to see these sorts of issues and kind of have that spidey sense to know where they might be. And both Google, Facebook, Apple, OpenAI, all of them, and probably a few other companies that I haven't listed, Microsoft and IBM, they all do have dedicated ethical AI, responsible data science, whatever you want to call it, research teams. And I would say most recently, Mozilla just announced that they had given out, I think, 8 to 10 fellowships for academics to come on and, you know, be paid to do research in this area, build software in this area. So it's definitely something where it's growing in interest. Specifically in Google, I think that team's been very controversial, though. I will highlight that because the two main directors in that organization were fired, or they were voluntold to quit because their work was actually pushing a little bit too much against the work that Google was doing with large language models and certain search engine optimization approaches. And I think just kind of goes to highlight how a lot of this work, in addition to being very interesting and valuable, it also could kind of put a target on your back, because oftentimes you're going to be the person saying, no, we should not do this. Or if we want to do this, we need to invest more resources to make sure that we do it right. And in these companies, which are primarily growth oriented, build fast, break things, et cetera, you're going to be butting heads.
Yeah, and Rachel already sent the Wired article about the Timnit Gebru. Yeah, if folks you are interested, this is So they were Google ethical AI team leader, I think. So they fired them. So I think we can continue this thing and like a forever, but it's time. I would like to be respectful of the time. We are already past our time for 3 minutes. Grant, thank you so much. This was really, really very good talk, and maybe we can have you again. Maybe we can have we can meet again in some other context. But this was really great talk. Thank you so much. I really learned a lot.
Of course, happy to give it, and thank you so much, everyone, for having me. And Murat, thank you for the invitation.
Of course. And folks, again, you will get the recordings and the slides from our team. And in the meanwhile, if you would like to learn more about the data science program, you can check our website, okay? And you can always reach out to me through email, okay? Thank you so much for joining. Enjoy the rest of your day and have a nice weekend, okay? Take care.